So guys, this is the first thing we need to talk about is the homework assignment. You wrote it down last time, obviously. So relative to question number 21, but this isn't the only place this sort of reared its ugly head. Guys, we run into a problem in the way that the questions at the end of the chapter are worded, especially relative to chapter 19. The problem is this. For example, in question number 21, the question that they're specifically asking you, it's a two-part question, is relative to delta E, which is change in internal energy, right? But the problem is that change in internal energy is a function of work and heat. But what we said in chapter 5 is we're getting rid of work, and then we talk about enthalpy because we're disregarding the opportunity for heat. Then in chapter 19, they totally backpedal and they start talking about energy again, and the things that we've been learning about enthalpy and spontaneity and things like that, all of a sudden, when we read questions like number 21, and this was, I got the answer wrong on the key, because as I read question number 21, I was thinking, I'm answering this in the context that we taught it, and we taught this through the context of enthalpy change, delta H. The question is specifically about delta E, and by looking at this through the lens of delta E rather than delta H, the answer changes. Because delta E allows for the possibility for work, and it completely changes the landscape of the question. So here's what we're going to do. On question number 21, we are going to rewrite that question, and we're going to change the delta E to delta H. Then the question is more in keeping with what you need to know relative to the AP curriculum, and things make more sense. So, and guys, as you're going through the homework then tonight, because you're going to do all of this tonight, the part of it you haven't already done, if you run into delta E's, please make note of those, change them to delta H's, because this, well, we should be careful. At least make note of it, and then let's talk on Wednesday and see whether or not it's appropriate to have changed those delta E's to delta H's. But understand, you need to understand spontaneity not through the lens of delta E, but through the lens of delta H. Is that okay? Okay, so guys, let's then talk about Wednesday really quickly. Your tests are graded. You will notice that they are not in the grade book, and they won't be. Because when you get your test back on Wednesday, you are not going to see the score that you get on this test. When you get this test back on Wednesday, the score that is written on that test is actually the score you would have got were this an AP test. Right? Which means you're not shooting for an A. You guys understand that, right? You are not shooting for an A on the AP test. You're shooting for a good solid C because that's a 5. So, guys, what you're going to find out is that when you get this test back on Wednesday, we're going to spend the entire class period and we're just going to rewrite those tests. Okay, so we're going to finish up entropy today. We're going to spend Wednesday rewriting this test. We're going to take Friday. Let me look. We may wrap up this unit on Friday. Right. Let's talk. So we'll see how Friday goes. Friday we're going to have to hold sort of loosely. If we finish the unit on Friday, your test will be Tuesday. If we bleed over into Tuesday, your test will, of course, be Thursday. But in either case, the one thing you can be sure of is we don't have a test on Friday because we are going to spend a day next time and rewrite the test. So maybe what I could do is let me look into my crystal ball here a little bit, and let's see how this shook out last year. So this is last year's website, and if we go to AP and then go back to September, we did entropy, rewrote the test, quantifying entropy. No, we actually broke it up into 2 days last time. So that'll probably be the case. You guys are largely on the same track that my class was on last year. So I think you can rest fairly comfortably that your test will be Tuesday or be Thursday, unless we just get in here and we find out that you guys just run right through how to quantify entropy, in which case we'll take the test Tuesday. Okay? All right. So with that said, guys, any questions about calendars and stuff like that? Y'all are good? Okay. So guys, let's pick up where we left off. So last time, you may remember, we finished up the day by talking about this dropping egg. And as we were doing that, we talked about the idea of reversible, irreversible, and spontaneous. So guys, let's remind ourselves about what those terms mean. So guys, let's do reversible first. If we've got a reaction that's reversible, what does that mean? Good, so done and undone through exactly the same process, and you already knew a term that describes a reversible process, equilibrium. Okay, so then guys, we talked about irreversible processes, and irreversible processes are processes that cannot be undone by simply turning the direction. Guys, does that mean irreversible processes can't go backwards? No, but what is true about the reverse process? Different pathway, which means different amounts of work and heat. And that was the idea with the egg. So when you take an egg and you drop it, it hits the counter and splatters. That is the direction that always happens. Because guys, you know that splattered eggs don't just magically reform and rise. But you did learn something surprising. So guys, when we drop the egg and it goes splat, is that endo or exothermic? Gives off energy. How do you know it gives off energy? Because it happened. Right? All spontaneous processes give off energy. You okay with that idea? So guys, everything that you see, everything that you know happens has got to be it's got to give off energy. And so when you drop the egg, it goes smush splat or splat smush, depending, and you got a pile of yuck. And we know that gave off energy. Now, can we take the pile of yuck and turn it back into the eggs? Yeah. And how much energy does that take to turn it back into the unbroken eggs? Same amount of energy. The difference is the distribution of work and heat. So guys, when the egg splats, there's a lot of heat that is released, and then there's a little bit of work because it makes sound. But guys, in order to put those eggs back together, it's going to take a lot more work, as Jake said, indicating it's a different pathway. You guys okay with the ideas? Okay. Now, what does this have to do with spontaneity? Well, guys, every process, whether it's a chemical reaction or an egg falling from a hand, has a spontaneous and a non-spontaneous direction. So eggs always fall. That is the spontaneous direction. Do eggs ever magically come back together? No. So that is the non-spontaneous direction. So guys, the big idea then is this. We've got reversible and irreversible. If it's reversible, it's at equilibrium. If it's irreversible, that means it has a direction that it always goes. That's the spontaneous direction. And it has a direction that it never goes on its own. That's called the non-spontaneous direction. And we now understand that the spontaneous direction always gives off energy. What do we need to talk about? Yes. But I mean, what do we need to talk about reviewing Thursday so you're ready to talk, as Jake said, about entropy today? You guys good? Okay. So then, guys, we had this awkward conversation. No, you can't do it now. We had this awkward conversation about the quick cold pack. Because guys, remember what we decided. Let's talk spontaneity and then let's talk enthalpy. So you understand now that this is a bag of ammonium nitrate pellets with a bladder of water on the inside. When you squeeze this, it crushes the bladder. The ammonium nitrate and the water mix together. And as the ammonium nitrate dissolves into the water, is that endo or exothermic? endothermic, and we know that because it feels cold, meaning that it's drawing heat energy out of our flesh and into the reaction. So that makes this endothermic from experience. What about spontaneity? Is that process spontaneous? Yeah. What about the fact that I've got to crush it first? Does that mean that something has to happen to it and therefore it's not spontaneous? No. So what's our measure of spontaneity relative to an initial input of energy? And remember, the idea, guys, is an initial input of energy is okay. The question is, do you need to keep inputting energy or it will stop? Remember, I think, Jake, you asked about the ball. Somebody, it might have been Mark or someone, asked about the ball rolling uphill. And we said, well, wait a minute. If we got to push the ball uphill, right? But we still have to push it from the top if it's perched on the top to get it to go. And we talked about the idea that if the, oh, I need my writing tools. Hang on. We talked about the idea that if we have a ball that is perched on the top, yeah, we have to give it a push. But after we give it that initial push, we don't have to keep pushing. It will roll downhill. Contrast that with a ball that is sitting right here. Yeah, we can give it a push and we can move it uphill. But guys, as soon as we stop pushing, what's the ball do? Stops going uphill. So that is our test for spontaneity. So guys, let's go back to this then. Is the dissolving of the ammonium nitrate into the water spontaneous? Yeah, and now we've got conflict, right? Because it is spontaneous and yet it's taking in energy. And we talked about the idea that any process that happens has to give off energy. And now we've got a process that's taking in energy and it is spontaneous. So you guys all back with me to that tension? So now we're ready to talk about it. So guys, so this is everything we talked about with the egg drop. We answered all these questions. But then guys, let's make sure we're clear on these take-home messages. Take-home message number 1, spontaneous processes have a direction. And what do we call that direction? The spontaneous direction. And so guys, that means that spontaneous processes are irreversible. Again, you got to remember Jake's understanding of irreversible. That means they can't go backwards through the same path. Yeah, they can go backwards. It's just a different pathway. And now guys, relative to this idea of our quick cold pack, we've come to this impasse. And the impasse is the idea, well, actually this isn't it. The impasse is this, that enthalpy change is not enough to determine whether or not a process is spontaneous. Because we understand that if a process is spontaneous, the reverse process is never spontaneous. But energy change alone, or at least enthalpy change alone, is not enough to tell us if something's spontaneous. So I'll let you catch up. We'll do questions. And then we will dig in and solve this problem. Let everybody catch up because some of your classmates are very dutiful note takers. See? You don't get props for that though because I printed it for you.
Okay, fine.
I know, because you could have blamed me because you were saying I didn't put up the link, but it was the previous link. It just keeps going and going. Okay, you guys all caught up? So guys, let's do questions and then let's transition. Brandon, go ahead. Okay, so here's the idea. And you may remember our list. We talked about 3 different changes. Interestingly, I don't remember our list. I know one of them was a rusting nail. One of them was hydrocarbons burning. Oh, and the other was balls rolling downhill. So we've got this idea that When we had that conversation, we said balls roll downhill. Why? They're losing energy. We said hydrocarbons burn. Why? They're losing energy. We said nails rust. Why? They're losing energy. And so we developed this idea that when we think about losing energy, we think about losing energy in the form of heat, because we've already got rid of work. And so if work is gone, now we're left with heat. And so when a ball rolls downhill, how does it lose energy in the form of heat? Well, friction as it rolls, and then if there's air, certainly air friction as well, but there is a release of energy in the form of heat. It's also pushing, and then we talked about burning hydrocarbons. I mean, you can feel the heat. It warms our house. And then we talked about the rusting nail, and we said, yeah, actually rusting nails do release heat, and if we grind them up fine enough, and this was the conversation you and I had, that we make hot packs out of those, right? And so we know that all of those things lose heat. So we established this idea that said spontaneous processes lose energy in the form of heat. That's what led us to this, because this is a spontaneous process that appears to be taking in energy, because this doesn't give off heat, it takes in heat. So this is definitely endothermic, but it's also definitely spontaneous. And so that's what leads us to this thought, that we developed this broad statement that said spontaneous processes give off heat. But now we understand that some spontaneous processes take in heat. What that tells us is that enthalpy changes, endo and exothermic, are not enough to tell us if a process is spontaneous. You guys good with that? Okay, so now guys, let's unpack the actual answer to this question. So, is it true that spontaneous processes are always exothermic? Think through that. Is it true that spontaneous processes are always exothermic? That is not true. Again, that's the quick cold pack. But guys, what about this question? Is it always true that spontaneous processes give off energy? Yes. So now what we've got to do is we've got to link those two ideas together, because it is true that spontaneous processes give off energy. It's just the energy that they give off is not always in the form of heat. And it's also not work. So what could it be? It's entropy. So guys, now let's talk. And this is going to sound like sci-fi babble, ridiculous, give me a stinking break, you got to be kidding me. I mean, guys, you can picture heat. You can picture something burning. Experientially, you get heat. And you get that heat goes away and that makes things happen. But guys, entropy is harder to understand. It's harder to visualize as a driving force that causes reactions to happen. But guys, you gotta just get comfortable with this. Entropy is very real, and it is very much a driving force in our universe. So guys, what on earth is entropy? It's right there. That's all it is, guys. It's randomness. So we're not even going to use the word entropy yet. We're going to use the word randomness. So what we are now proposing is that randomness is a driving force in the universe. Let me convince you of it. So guys, here's what we've got. You don't need to draw this, and it's actually a much better drawing in the book, but here's the idea. So guys, what we've got here is we've got two rigid containers. Please don't imagine that these are balloons. They won't collapse. They're metal containers. Imagine, if you will, that we took... Did I almost put out your eye, Anna? We may need to get you goggles. That's awesome. Thank you. So guys, imagine that it's actually this. So we have, and I'm not going to rip the lids off of these, but there's actually, let's not do that, but there's a little valve in there. So what we're talking about here is one canister of gas One canister of gas that's got gas in it. And then imagine that this canister was empty. It's not. But just so you understand what we're looking at here, we've got two rigid canisters. So when we empty one of these canisters, it's not going to collapse, right? It's rigid. So one has got 1 atmosphere of gas in it. The other one is empty, and they are linked together like schnozzle to schnozzle. Okay? Little hot glue, we're there. Okay, so we've linked them together nozzle to nozzle. Now, here's the question. One of these canisters is empty. The other canister has got an atmosphere of gas in it. What happens when we open the valve? What does this gas do? Spreads out. And when we allow this process to stop, what's eventually going to happen? What's it going to look like? We're going to end up with half of the gas in one container and half of the gas in the other container. Now, guys, what do we have to do to make that happen? Do we have to squeeze this? Oh, sorry, don't touch the board. Do we have to squeeze this container to get that gas to move over? No. Do we have to heat this gas up to get it to go over? What do we have to do to get half of this gas to go over there? Just open the valve and it happens, wait for it, on its own. It's spontaneous. But now, guys, here's the question. What happens to temperature when this process takes place? And the answer is nothing. This is what is called an isothermal process. Energy does not go out. Energy does not go in. The temperature doesn't change, which means what is not exchanging? Heat. But it happens all on its own. So guys, now we've really got a crisis because we've got a process which we know to be spontaneous because we ain't got to do nothing but open the valve and it goes, and energy doesn't go in or out in the form of heat. But guys, here's the trick. It is happening. Therefore, it's spontaneous, which means that there is actually a decrease in energy. But that decrease in energy does not come through the avenue of heat. Where is the energy actually changing? What is changing? What is the driving force that causes this to happen? Go ahead, Jake. It's randomness. Guys, randomness is forcing this to happen. It happens every time, and you don't have to do anything to make it happen. So if you were to come up on a situation like this, and you were to go, and you understand experientially this is going to happen. You open this thing up, that gas is going to expand, and you're going to end up with a 50-50 spread. But guys, why does it do it? What is forcing that to happen? And the answer is randomness. Now guys, here's the trick. Is randomness going up or is randomness going down? In this. So, let me ask you this way. Let's go top and bottom. Which one is more random, the top system or the bottom system? The bottom system is more random. And now guys, I'm not going to ask you to read this, but if you would like a better discussion about why the bottom system is more random, if you turn in chapter 19, and some of you are going to like this, and we'll do a little bit on it, but let me show you where this is. I don't think they, hold on. Seven 787. It's not that. Let me try 794. They may have taken it out. You know what? Actually, as I'm thinking about it, it's not in. I was thinking it was going to be one of those closer look things. Maybe they moved it into the text. There it is. Yes, it's at the top of the page on 7. Oh, look at that. They even made it its own little thing. That's really cool. So guys, that diagram at the top of 794, let's talk about it really quickly so that you understand how it is that the bottom system is more random. So it goes like this, and I'm just going to do this exactly like they have. So guys, let's, you know what, if I use colors, this is going to be tough. I'm going to use symbols. So we're going to do an X for one molecule, and we're going to do an O for the other. So guys, when we start this process, and we're going to say that instead of an atmosphere of gas, there's only two molecules, molecule X and molecule 0, okay? So before we start this process, these molecules have no choice where they are. They're in the right-hand container, they are X and they are 0, and they're trapped there. But guys, what are those molecules actually doing? Flying around at hundreds of miles an hour, right? If they hit the wall, they bounce back. If they hit each other, they bounce back. If they hit the valve, they bounce back. But now what happens if the valve is open and therefore no longer a barrier? Well, if they hit each other, they bounce. If they hit the wall, they bounce. If they hit where the valve used to be, what do? They go through. Now they have, and this is the way we talk about this, they have greater degrees of freedom. They have more places that they can be. So now, guys, what we end up with is all sorts of different possible options. So when that valve is open, we still could have this. We could have X and O in the same container. But we could also have this scenario where X is over here and O is over here. But what's our other scenario? Well, we could have X and O over here, but then, guys, what's the fourth scenario? X and O on the left. But now, guys, here's the trick. Which one of these scenarios is more likely? A scenario where they're clumped together on one side or the other, or the scenario where they're spread apart? Spread apart, right? So in theory, this would, let me switch colors. In theory, this would happen a fourth of the time. This would happen a fourth of the time. And then this, which we're going to consider to be spread out. And it doesn't matter if it's one or the other in one, they're still spread out. You see what I'm saying? One in each. So guys, that's 50% of the time the way that it'll be. So already with only two molecules, we're finding that the most likely arrangement is with these things spread out evenly, half and half. That doesn't mean that they couldn't be both here and both there, but just by the law of averages, 50% of the time they're going to be evenly spread out half and half. Now guys, what if we add a third atom? Well, then all of a sudden we find that there are many more configurations. What if we add a fourth atom? Well, now if we've got 4 of these things, we're going to find that the situation that is most likely is 2 and 2, but that 2 and 2 distribution is more now than 50% because of all the possible permutations. Now, guys, when we jack that number of atoms up to Avogadro's number, all of a sudden you find out that the possibility of you having a mole of gas over here and none over there, or a mole of gas over there and none over here, functionally falls to 0. And by looking at those possible distributions, you find that most of the time, functionally all of the time, they will be evenly distributed, and you get closer and closer to that possible asymptote with the more and more molecules you have. Does that make sense? So guys, the idea then is that we can understand this idea of randomness and possibility. We can understand it mathematically. But guys, these are not just mathematical tricks. Guys, atoms don't know how to do fractions, right? Because you got to understand that math never forces things to happen. Math describes things that happen, and we find out mathematically what we already understand experientially. And the thing that we understand experientially is that when we open up this valve, the gas spreads out. And guys, that happens because of randomness. And you're going to find out in a minute that randomness is called entropy. So guys, we just need to pause for a second and get really comfortable with the idea that processes happen because they are moving to conditions of greater randomness. So how do we understand randomness? And guys, if you're trying to define randomness in your brain, randomness is a function of choice. That's not going to come up in the notes, but you may want to include that. Guys, randomness is a function of choice. So now let me share with you the pain of parenting. I have a 15-year-old boy that has not wrapped his head around the idea, Tracy knows him, that has not wrapped his head around the idea that clothes go in drawers. He thinks he's got a lot of choices. See, in my little world, I hate randomness. In my little world, clean clothes go in drawers. And those clean clothes only have one choice. They go in the drawers, and therefore there's not much randomness. In Cody's mind, he's got a lot of choices. He's got shelves, he's got the floor, he's got under his bed, he's got on his desk, he's got left in the bathroom, he's got left on the stairs, he's got left in the dryer. There's like 11 different choices of the places he thinks clean clothes can go. As a result, his laundry world is much more random than it should be, because you could find his clothes in any one of those 11 places, where in fact we were working towards a much less random condition where those clothes should just be in the drawer. So guys, randomness is a function of choice. The more possible ways something can be organized, the more random it is. Does that make sense? You understand the idea? So guys, we're going to pause right now and see where you are with randomness. And then if you're comfortable not just with randomness and how we understand it, but that it's a driving force, we're then going to change its name to entropy and keep going. So is there anything we need to talk about relative to randomness? Go ahead. Yes. So, but understand, molecules can't do statistics. They would never pass Gilchrist class, right? So, statistics can describe what's happening, but it doesn't cause it to happen. Do you understand the difference? So, we understand that these molecules are going to spread out. And it's not because they're making choices. These molecules are just moving at hundreds of miles an hour, and the law of averages say that as they're moving randomly throughout this container, you're going to end up with a 50-50 split. We can describe that using pretty little pictures like that thing on 794, and we can also describe it statistically. But the reason that it happens is because these molecules are just moving randomly, and as they do, they fill whatever space they're given. I'm ready.
General science, we were taught the concept of, I don't want to say osmosis because
Yeah, go. Keep going.
So, Mr.
Hodges.
Mr. Pusey.
I love Mr. Pusey. Yeah, he's a fine fellow.
He kind of gave the example of perfume. He sprayed it into the room.
Correct.
And then that put the perfume
Yeah, right.
spread throughout. So
Absolutely.
everyone
Good.
smells it.
Good.
I never thought about that as that's particles moving so fast that they just fill the room.
And that's exactly why. So let's separate that in your brain, though, because that's not osmosis. Okay, osmosis is a separate process. It's also based upon random movement, but there's a pressure factor there. There's work being done in osmosis. Or, well, depending, either work is being done or the system's doing work. So when we talk about osmosis, we got to talk about work, and we're going to do that in months. But let's go back to your perfume example, because it's wonderful. The idea is that when you release that fine mist into the room, that mist, as Pusey so well described, it spreads out. And why does it spread out? Because it's just doing its perfume molecule thing. Those things are moving around. They're being batted about by the molecules in the air, and they spread out. Do you have to do anything to make them spread out? You don't have to. They just do it on their own, right? Why do they do that? Randomness. It's a wonderful example of how you don't have to heat them up. They just spread. There's no temperature change, but they do it on their own simply because of randomness. It's a great connection.
But isn't this where this is more orderly than randomness because you have half of them going there and you know them?
Okay, so on this or the perfume thing?
This and the perfume.
Okay, so let's do both. So which is more ordered, the top one or the bottom one?
The top.
Absolutely, and that's the point. So when a process goes from high order to high disorder, randomness is going up, and that describes why it's happening. We're going to talk about the second law of thermo, which says that processes that increase entropy tend to be favored, and so increase randomness. So this process increases randomness, and that's why it's happening. Same thing's happening with the perfume sprayer. When the perfume's in the bottle, it's very ordered. I mean, it's contained, it's a liquid, there you go. But when you go and you vaporize it, then entropy is going, randomness is going up, and that explains why it spreads out. It's all because of randomness, which we're going to call entropy. Go ahead.
So, like it doesn't care about entropy, right? It's just bouncing into molecules and moving around, and that's why.
Right. Right.
Is entropy always going to be moving of molecules like that, bouncing into each other? Like different.
You have no idea how much I hate the word always.
Always.
Can we use mostly? Oh gosh, I'm trying to think of all the places you're going to have to think about randomness. So is randomness always a function of motion? And I think you could fairly say that in our limited, the limited scope that we need to think about it, yeah. But let's do this. Couch that question for a second. We're going to look at a very specific example, and we're going to track randomness through the entire process. And as we do, I want you to be thinking, does this always map back to motion? And then we'll talk. Okay, so you guys okay with this idea of randomness? And the idea is Brandon's getting more comfortable with that randomness is a driving force. Perfume spreading through a room, gases spreading throughout here. You okay? Okay. Then guys, let's go back here. Why does this happen? So when we crush the bladder inside of here, the salt, the ammonium nitrate, dissolves into the water. We understand that it's taking in energy, which would seem to indicate that it shouldn't be spontaneous, and yet we know it is. So guys, bottom line, what is the driving force behind this happening? Randomness. Let's think about why. If you could picture, can you see the pellets if I hold it up to light? I actually kind of can. Oh, you guys can't. So guys, these ammonium nitrate, they're pellets. And if you could look inside of them, they would be very, very organized. They would look like this, right? Crystals. Guys, crystals have very low levels of randomness. These suckers are locked in place, right? They got nowhere to go. Crystal lattices, by definition, are not terribly random. But guys, what happens when that ammonium nitrate dissolves in the water? What do you picture when you think of dissolving? Yeah, the molecules come in, they rip those crystals apart, and as they rip those crystals apart, what happens to randomness? Randomness goes up. And as that randomness goes up, it is actually the driving force that causes this ammonium nitrate to dissolve in water. So what is it that explains this otherwise endothermic process to be spontaneous? And the answer is an increase in randomness. Go ahead.
So that's when a solid or crystal is dissolved in water.
Yes. Mm-hmm. Yep. Mm-hmm. Yeah, and it's, Mark, hold on to that question for a second, because you're going to find out what we just said about the ammonium nitrate is not as simple as we just painted the picture, okay? So, guys, do you understand now that we're saying that process of dissolving causes an increase in randomness because the ordered crystal comes apart? Is that okay? Okay, what I want to do then is I want to offer you this. I think this is going to be the best way to do this. Let me just exit out of this for now, move this aside. And guys, I don't have a video of ammonium nitrate dissolving in water. I do have a video of sodium chloride dissolving in water. So we're going to use that as just sort of our generic model of dissolving.
When an ionic substance, such as sodium chloride, is placed in water.
Okay, so let's go back. So there is our ionic substance. So guys, tell me about the randomness of that crystal. Does that crystal have high or low randomness? Low randomness, right? You'll find out in a minute it is a low entropy system. Now let's bring in some water.
Ionic substance, such as sodium chloride, is placed in water.
I think that's the best that I can do because obviously this video is intended to focus on the dissolving process. But guys, talk to me about the randomness of a sample of water. So if we have liquid water, is that a high or low randomness system? Kind of in the middle, right? Because what are these molecules doing? Well, they're moving around very rapidly, right? But what about in terms of their freedom, their options, like my son with his laundry? Do these molecules have a lot of options? They can be a lot of places. They could be here, they could be here, they could be here, they could be here, they could be here. They can even be out here if they evaporate, right? So guys, these molecules, especially relative to a solid, have a fair amount of freedom. They're relatively random. Now, guys, let's talk about this.
Water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice.
Trying to find a good place
The
to stop.
solvated ions move off the surface and become separated in solution.
Let's try that. There should be some chloride in there, but this is a better picture. So, guys, now let's talk about randomness. What is happening to randomness as this salt dissolves into the water? Is randomness going up or down? Oh, Anna, I love that you're wearing a tie. Say it again. Say it again. Ah, okay. So, but what else? Okay, so, but I heard a lot of you say, yeah, randomness is going up. What were you thinking? Okay, so now what we're understanding, guys, is we've got to look at the bigger picture. The answer to your question is no. But guys, there is not a law of conservation of randomness, okay? But just a second, Jake. So, guys, what I want to do is I want to invite you into this new idea that says when you're thinking about randomness, and Mark, this is why I sort of hesitated at your thought. Guys, when we talk about randomness, you've got to understand that you've got to open up your view a little bit. Because, guys, we've got some processes here where randomness is going up. But as Anna so insightfully pointed out, we've also got processes where randomness is going down. So now let's talk. Guys, what is happening to the randomness of the sodium and chloride ions as it dissolves? Randomness is going up, right? Initially, these ions were trapped in the lattice. They had very low randomness, not much choice. They were stuck. As they dissolve, those ionic bonds are being overcome. They're being carried off into solution, and all of a sudden, they're like birds getting kicked out of the nest, and they've got all sorts of different options. But as Anna pointed out, that's not the only thing going on, because guys, look at the water molecules. They enjoyed a very high degree of randomness when they were simply a liquid. But when the salt dissolves into the water, what happens to the freedom? What happens to the randomness of these water molecules? Is it going up or down, Anna? It's going down, right? Because these water molecules are now locked around these ions, losing a tremendous amount of freedom that they previously enjoyed. And now the randomness of these water molecules is going down. Now, Rebecca said something interesting. She said, is there the possibility that the amount of increase in randomness for the salt, the sodiums and chlorides, would be equal to the decrease in randomness for the water molecules? And the answer is absolutely not. The world does not work that way. So there is no law of conservation of randomness. We are going to talk about the way the world does work in just a second. But guys, for now, I need you to understand that when we look at randomness, it is not enough to just focus on one particular component. In this example, the salt. We've got to look at the entire interaction, because many times we'll have competing increases and decreases in randomness all in the same system. Because our system is not just the water and it's not just the salt, it's both. And we actually have an increase and a decrease in randomness simultaneously. So what we need to understand now, the point of that was that we've got to look at the bigger picture. You okay? Go ahead.
So are there, the degrees of freedom increase because there are more possible configurations of which molecules are connected to which ions?
But once they're connected, they lose that freedom. And that is not to say that these water molecules are always the 6 water molecules clamped around that particular sodium ion. But to the degree to which these water molecules are no longer free to move on their own, there is certainly a decrease in randomness. Is that okay? Okay. All right. So guys, you sold on that idea about context and increase and decrease simultaneously? Okay. So how then do we make sense? How do we make sense of all of this then? Well, guys, it's now time to bring this together. So, and don't write this down yet. I'll key you on the thing that we do need to talk about. So we've got this idea of randomness being a driving force, and we understood that this is isothermal, meaning that energy was not going in and out in the terms of heat. Iso is isolated, and thermal, of course, is heat. So guys, we are now ready to talk about this in terms of spontaneity. So would we ever see this process go in the opposite direction? What if we were to flip the containers, and if we were to say we started with half and half, so if there were a barrier in here, and if we started with half and half, and then if we removed the barrier, would it ever go back to this? No, so we've got a definite direction, right? And because we have a direction that it always goes, and we've got a direction that it never goes, we know that this is irreversible and therefore spontaneous. So now, guys, let's link this together with the idea of spontaneity. And guys, the idea then is this last sentence, and you may want to write this down. Processes in which disorder or randomness increases tend to occur spontaneously. Okay, so guys, now let's talk about a new tension that we've created. So here's what we now know about spontaneity. Processes that are spontaneous tend to give off heat. That's exothermic, right? Now we're saying processes that are spontaneous also tend to increase disorder. You good with that idea? Okay, so guys, which one is it for this? What's the driving force? Is it because it's exothermic, or is it because disorder goes up? Disorder goes up, right? I think some of you are probably thinking ahead then and saying, how does this play out? What if we've got a process that is exothermic and gives off, is exothermic and entropy goes up? What if we've got a process that is endothermic and entropy goes down? Do you see how we have these two variables now, these two switches? We're going to answer that tomorrow. Well, actually, no, Friday. Because we now have two indications of spontaneity. We know that they're exothermic, and we know that entropy goes up. And you're going to find that those can work for or against each other. And we're going to solve that on Friday. For today, to wrap up the day, we're just going to dig into this idea of randomness. So guys, bottom line is processes that increase randomness tend to be spontaneous. You good for now? Okay, so here we go. Let's not talk randomness anymore. We're now going to use the actual term, and the actual term is entropy. So guys, entropy is the disorder of the system. Let's say this right now. Do not ever think about the order of a system. Ever. Because it will screw you up. So guys, understand you have always got to think about disorder. So guys, why is it important to think about disorder rather than order? Well, you ready? Try this. If my son takes his clothes and throws them all around the room, what happened to disorder? Went up. What happened to order? Went down. So which one is it? Is it positive? Is it an increase in disorder, or is it negative? Is it a decrease in order? And guys, understand that it seems trivial, but when you start doing math, positive and negative is not the same thing. So we will always think about this through the lens of disorder, meaning that an increase in disorder is positive, a decrease in disorder is negative. Understand, if we were thinking order, the signs would change and it screws everything up. So guys, you got to understand this through the lens of disorder. So how do we measure disorder? We measure it using the term entropy, and entropy is abbreviated S. Which is obvious, right? Entropy, S.
I thought you were being for real right
Yeah,
now.
no, it's... And yeah, well, in the same way that heat is Q and enthalpy is H, right? It all just makes sense. It's exactly, we need our abbreviations to have high entropy. So guys, this then is the idea. And again, this is why we think about disorder. The more disordered or random a system, the larger its enthalpy. You okay? You good on that? Because this is about to go away. I'm going to switch to the next slide. So, and you're also comfortable with the idea that when we think about disorder, as we saw in the salt video, it's not enough to just think about the salt. We got to think about other things as well. You good? Okay, here, let me just show you, because frankly, that's what this is all about. So we did the dissolving of water, and we talked about the order and the disorder. Okay, so guys, then the question becomes, how do we talk about order? How do we talk? We don't. How do we talk about disorder? Well, guys, here's the idea, and this is what we got out of the video. Unlike enthalpy changes, guys, when we talk about entropy changes, we got to talk about the system and the surroundings. It's not enough to look at the water. It's not enough to look at the salt. We got to talk about all of it. So guys, when we talk about entropy, we are going to talk about what is called the entropy change of the universe, delta S sub universe. I know, right? Okay, so you ready for the world's most obvious equation? About this. When we do this, this takes into consideration the enthalpy changes for everything. So here you go. Change in entropy of the universe is equal to the change in entropy of the system plus the change in entropy of the surroundings. You need some clarification? Okay. Yes, yes. Okay, so guys, what does this then mean? Well, you ready? In any reversible process, we're almost done for the day. In any reversible process, and remember reversible means equilibrium. You're picturing it going in both directions at once. In any reversible process, what do you suppose is true of the entropy change of the universe? If it's reversible. Think about it. So remember reversible. What has to be true of a reversible process? Not just forward and back, but through the same pathway. So if a forward process and a backwards process are just repeating themselves, what would be true of the entropy change of that overall process? It's going to be 0. Doesn't that make sense? If the forward process increases entropy and the reverse process is exactly the opposite, it will decrease entropy by an offsetting amount, and the change in entropy is 0. And vice versa. If the forward process decreases entropy, the backward process will increase entropy. They always offset each other. So, the change in entropy for the universe is 0. Now, guys, order is conserved. But now Rebecca's saying, wait a minute, I just thought you said there wasn't a law of conservation of entropy. This only works in equilibrium reversible processes. So guys, what about everything else? And guys, everything else goes like this. In any spontaneous process, what do you suppose is going to happen to entropy? Up or down? Up. The entropy change for the universe has got to be going up. Guys, order is not conserved, and the entropy or disorder of the universe is always increasing. What's that? Oh, yeah. Well, my son could play that card, right? Dad, I'm not a slob. I'm just going where the universe naturally leads me.
I feel like, oh, they're not accepting the base problem.
That's right. Finally, you released its entropy. You just gave it what it was looking for.
It's just the entropy is trapped in there. The universe's energy is trapped in space.
There you go. So guys, there you have it. Next time, we're going to unpack all of this stuff, and we're going to bring it all together, and we're going to bring together enthalpy and entropy, and we're going to talk about all these interesting situations where one is favoring spontaneity and the other is not. That's called Gibbs free energy. But for now, let me leave you with a thought. I was considering not doing this because it's likened to child abuse when Brandon hears things like this because his head explodes. But it's still fun.
Okay, I'm ready.
So guys, try this on for size. What do you know for sure about everything that you see going on around you in this world in your day-to-day life? They're all spontaneous. Guys, think about that. Everything that you see happen around you has got to be a spontaneous process, because if it's not, it wouldn't happen. Now you're saying to yourself, wait a second. Well, balls don't spontaneously roll uphill, but I've seen balls roll uphill. This is where this gets a little deep. But guys, check this out. Can we make balls roll uphill? We can push them, right? So now instead of thinking about the ball rolling uphill, we need to find the spontaneity in balls rolling uphill. So what does it take to make a ball roll uphill? Well, it takes somebody like me pushing it uphill. And if you see me pushing it uphill, then you know that the biochemical processes that are happening that allow me to push that ball uphill must be spontaneous. So now you're thinking, well, no, they're not, because if you don't eat and die, you can't push balls. So now we track this back to the food that I eat. And so that food must be the decomposite breakdown, like glycolysis of that food, right? Cycle stuff in biology. Well, that must be spontaneous. Well, no, that's not spontaneous because there's got to be an energy. So guys, if we track back far enough, eventually all processes that you see happening here on the earth can be tracked back to what? The sun. Right. All of the energy, and I mean, I know there's other sources of energy. I mean, we've got cosmic rays, but those don't really fuel our Earth. We don't ever like set out, our garden and expose it to cosmic rays and expect it to grow. So we sort of expect that our source of energy is the sun. So guys, this is the deep thought. Our sun is not just a source of energy. It's also a source of entropy. Because as this energy travels from the sun to the earth, fueling every process that we see happen here on the earth, guys, we understand that energy that's being transferred through radiation causes non-spontaneous things to happen. But we've got this second law of thermodynamics that says any process that is spontaneous creates an increase in entropy where? In the universe. And so here's the deal, guys. Life itself, you ready? Life itself, by definition, is a violation of this idea that entropy is going up. Because our bodies are knit together out of the same stuff that used to be in the dirt when the cows ate it, and then we ate the Big Mac and it became us. So guys, life is an ordering process. And we also understand that life is spontaneous, right? That life happens. We know it happens because it's happening. So if life is spontaneous and this is happening, and if the second law of thermodynamics is true, then where is the increase in disorder that's got to be present? Because we know that life is an ordering process, and if life is causing a decrease in disorder, there has to be an offsetting increase in disorder somewhere in the universe. And where is that? It's the sun. So guys, our sun is not just a source of energy, it is also the source of disorder that allows life to happen. There you go, Brandon. I'm glad. So guys, here's your homework. We have about 5 minutes. No, what time do we get out of here? Right now? In 2 minutes. So guys, we will not, we'll grade homework on Wednesday, but we will not talk about Gibbs free energy Wednesday. We will do that Friday. Matt, don't leave without talking to me. Yeah.